Okay. So remember what we said before, there was the motor effect, and you put electricity in and you get motion out. Well, you also get the generator effect, which is we put motion in, electricity out. And the way this works is, well, the way we're going to look at this is using what's known as Faraday's law. Now what happens is if we have a magnetic field and then I have a loop of wire that if I change that loop of wire, if I change that magnetic field, then it's going to generate a voltage. And if it can, if there's a complete circuit, then current is going to flow around there. So what's the easiest way to change the magnetic field? Well, if, say, this playing card is my loop, remember what we said? We said this has to be at right angles to the magnetic field. If I flip this onto edge, suddenly there's no magnetic field going through that loop. There's the maximum possible magnetic field going through that loop. Now there's no magnetic field going through that loop. Now there's negative, no magnetic field. Positive magnetic field. So the easiest way is actually just to flip that loop around. And according to Faraday's law, the voltage generated is going to negative, and that comes from Lenz's law, we'll discuss that shortly. The number of the loops times the change in flux, and we'll discuss flux in a second, by the change in time, how fast it actually happens. Now what's flux? Flux is the magnetic field times the area, the amount of magnetic field contained. Magnetic field contained in an area. And in fact, if we talk about flux, flux is always how much of something goes through an area. So we can talk about magnetic flux, how much magnetic field goes through that area of that loop, or solar flux, how much light goes through that, or electric flux, how much electrical charge goes through there. Okay, so we're going to talk about magnetic flux. So flux is going to equal the magnetic field, and that's given in Tesla, times the area of the loop. And that's going to be in meters squared. And the unit for flux, for magnetic flux, is going to be Webers. So what we have here, this is flux in Webers. This is time in seconds. This is going to be number of turns, and that has no unit. And this is going to be the voltage generated, and then usually using Ohm's law, and if we know the resistance, then we can work out the current, and goes whizzing around there. So basically, the reason why it's negative is because this current, the direction of this current is going to be such that it opposes the magnetic field. And that Lenz's law basically says if you have a changing magnetic field, it's going to create a current, and the current is going to, that's what Faraday's law says. If you have a changing magnetic field, you create a voltage. If it can, so that voltage will produce a current. And Lenz's law says that current will produce, the current induced will produce a magnetic field opposite to the one that it's in. So the magnetic field generated by the loop is going to be going that way. Okay, so this is all very nice and good. And how do we actually use this? I mean, one way that this is actually used in real life is if you ever come up to the traffic lights, and there's often a sensor there that actually detects if there's a car there. What happens is the car has a big amount of steel, and it will change the magnetic field in the loop. So you have a basic magnetic field, you drive in, the magnetic field changes with time, that produces a voltage. There's often more than one loop. That produces a voltage. You have a sensor that picks up the voltage and says, there's a car there waiting for the traffic light. So, but let's actually try an example, exercise 5.4. We've got a bar magnet. A bar magnet is thrust into, it's pushed into a single loop of wire. Loop of wire that has a radius 6 centimeters. At the average value of cos theta, and remember the reason why we have that cos theta, sorry I forgot to put that in, no, cos theta, the reason why we have that cos theta is it like that or is it like that? That's going to be 0 degrees, that's going to be 90 degrees. Remember, at 0 degrees that's going to be maximum value, 90 degrees it's going to be 0. Okay. Radius 6, if the average value of b cos theta, isn't that nice, it's already worked it out for you, changes from 0.05 Tesla to 0.25 Tesla in 0.1 seconds. What's the voltage? Is the potential difference. Okay, so first things first, draw a picture. Okay, so we draw a loop. It's meant to be circular. We have a bar magnet, and we're going to push that bar magnet into that loop. Now we know that V equals number of loops, change in flux over change in time. And remember what's really important here is that whenever it says change, it's equal to flux final minus flux initial, change in time. We know what the change in time is. It's change in t equals 0.1 seconds. What's the change? What's the initial? What's the final flux going? Well, there's several things we have to know here. Flux final is going to equal B final times the area. So first thing we have to do is work out the area. What did we say that was, radius or diameter? Radius 6 centimeters. R equals 6. So we convert that to meters, because if in doubt always go to meters. So area equals pi r squared, which is equal to pi 0.06 meters squared, equals calculated time, pi times 0.06 squared equals 0.01131 meters squared. That's cool. So we have this change in magnetic field because the magnet is coming in. So B final is equal to 0.25 Tesla times the area, which is 0.01131 meters squared, equals 2.827 times 10 to the negative 3 Webers. Flux initial equals B initial, which is equal to 0.05 Teslas times 0.01131 meters squared equals 5.655 times 10 to the negative 4 Webers. Okay, so now we've got the final flux, the initial flux, we know what the time is, N equals 1, so the voltage is going to equal 1, a negative 1, flux final, which is 2.8827 times 10 to the negative 3 Webers, minus 5.655 times 10 to the negative 4 Webers, all over 0.1 seconds. Okay, so divided by 0.1 equals 0.02262 volts negative, which equals negative 22.62 millivolts. Yeah. So this is probably the most common way of generating electricity in the world at the moment. Basically what we do is we have a magnetic field, then we have lots of loops of wire which we then hook up to, I don't know, a steam turbine or such like, and then we spin these loops of wire, and as these loops of wire change, maximum magnetic field, zero magnetic field, maximum magnetic field, zero magnetic field, generates voltage. That voltage we can then will generate a current. And basically that's the heart of every, or just about all electrical generators, is they work on the fact that you spin loops. So maybe 80-90% of the world's 80 to 90% of the world's electricity is generated this way, is by spinning loops through a magnetic field.